Okay, so we're off to 1.3. Hopefully you read this before we're going to review it. So far the number systems we've seen so far, which is the Romans and the Egyptians, and the caveman, right, tally marks, have so far they use different symbols and numerals to denote large numbers, right? That's how they do it, different symbols. But they do not use position, right? Position is not used. That's why they are additive systems and not place value systems. Using 21 and 12 as an example, in our numbering system, the numeral 2 and the number 21 represents two tens because of its position, while the numeral 1 and 12 represents 110. This is the Hindu Arabic number system. It's base 10, just like the Egyptians, but position matters. So it's called a place value numbering system. So this is 1.8, example 1.8 in your book. You can pause this and read it if you haven't. You should read through the book before you watch the video. Okay, so this one here, they're asking what do the numerals and the number 75,963 represent? And they give them to you right here. So in other words, that's 7. That numeral 7 represents the number 70,000. And here's our place value system. The one you know and love your whole life, right? Just a couple words. This is the numbers in numbers, right? Moving from left to right. Moving from right to left, that's 10 times bigger than that. And 100 is 10 times bigger than 10, and 1,000 is 10 times bigger than 100, etc. Moving the other way, they're 10 times smaller. This is just a way of representing the numbers in exponential notation. It makes it's good shorthand, right? These are just exponents. So 10 to the third is 1,000. 10 to the fourth is 10,000. This basically means 1 followed by 4 zeros. Or it also means this, 10 to the fourth means 10 times 10 times 10 times 10, right? Just a little note about anything to the 0 power. Let's do 5 raised to the 0 power. That is 1, by definition. 7 raised to the 0 power. That is 1 by definition. That means something like 12 raised to the 0 power is equal to something like 27 raised to the 0 power, because any number raised to the 0 power is 1. Even a fraction like 1/2 raised to the 0 power is 1. These here. These here is anything raised to the first power is itself. So 5 raised to the first power is 5. 8 raised to the first power is 8. 1/2 raised to the first power is 1/2. So that's the distinction. I want you to understand these. And the rest are pretty simple. Well, let's do example 1.8a. So here it's asking, this is the one you have to do. Here it's asking for what do the numerals in the number 807,407 represent. So I'm going to start with the 8. The numeral 8. That is not the number 8. That number is 8 10,000s. So 8 of those. And a good way to put this in is just start from the back There's 7's going to go there. A 0 is going to go there. A 4 is going to go there. A 0 is going to go there. A 7 will go there, and an 8 will go there. See, I made a mistake. It's not 8 10,000s. If you don't write it in, it's hard to see what it is, right? And it's 8. Let's just rewrite it. It's 8 100,000. You may think I did that by accident, but I rarely make an error. I just wanted to lay it in first to show you how important it is. So I have 8 100,000s, and the numbers are put together with plus signs. 7 10,000s. And then I have, no sense of adding 0. 0 thousands is a 0, so I'm just going to skip that. Plus 4 100ths. Plus 7 ones. So there is what each numeral represents in the number 87407. Okay, what is the standard form of this number? This is actually pretty cool. You want the standard form of that number. Remember that caret means raised to, so I'll do the first one, 3 times 10 raised to the 4th. That's the same as 3 times 10 raised to the 4th. That's what most calculators use to raise to a power. So I could do this the long way, or I could do it the short way. Let me pause for a minute and clean this up here. Okay, so now we have these numbers that we want. We know what that is. Here's the long way of doing it. 10 to the 4th is right here. So that's 3 10,000s. This is a long way of doing it. Plus 2 10 to the 3rd thousands. Plus 4 hundreds. And then plus 8 ones. But let me show you a quicker, so that's, we could actually add those. We got 32,408. Now here's a quicker way of doing it. I'm just going to look at these numbers right here. I'm starting with 3 into the 10 to the 4th place. So I'm just going to put a 3 there. Then I want 2 into 10 to the 3rd place. I'm going to put a 2 there. Then I want a 4 into 10 to the 2nd place. I'm going to put a 4 there. And then I want an 8 in this place. So I'm going to put an 8 there. A lot of students will put the 8 here. There is nothing here. There are no 10s. There is no 10 to the 1. So there's the number. And see how easy it is to write out that way? Just a note, any number raised other than 0 or raised to the 0 power is 1. And we went over that before, right? Any number raised to the 0 power equals 1. So this is the thought question you have to answer for your homework, for your pictures. So if we continue the table to the right, that means if we continue it this way. What is the next power of 10? So here's the powers of 10. What's the next power of 10? What goes here? Here's the decimal. Decimal's got to go here, right? So what's the first place to the right of the decimal in power and exponential notation? Well, look, it goes 4, 3, 2, 1, 0. What do you think? Should I play some music and let you think? Or you got it? If you did, great job. 10 to the negative 1. And negative, that's not a negative number. This is not going to give you a negative number. It's just a negative exponent. Like 10 squared means multiply by 10 two times. 10 times 10. 10 to the negative 1 means divide by 10. So let's look from here going this way. And we're going to put in what the number is here. Start with 1,000. If I divide 1,000 by 10, I'll get 100. If I divide 100 by 10, I'll get 10. If I divide 10 by 10, I'll get 1. If I divide 1 by 10, I get 1/10. 10 to the negative 1, if you put it in your calculator, 10 raised to the negative 1, you will get 1/10. Or you might get 0.1. So that's the answer to that, and this is good insight. So let's carry it one more place, just for giggles. And this is going to be 10 to the negative 2, which means take 1 and divide it by 10 two times, which is 1 over 100. In decimal notation, 0.01. So here's the reading, just a little historical note. Our base 10 system, our base 10 place value system, what we use today, was created by Hindu mathematicians in the 1st century of the Common Era. They use the Common Era now instead of AD. And uses 10 basic symbols, numerals, whose shape has evolved over time. And here's how it's evolved over time. These are the shapes as they evolved over time. Of course, this is what we use today. But in the medieval ages, they used these numerals to represent these numbers. So here's 1.8b, and you'll be responsible for providing the answer in your homework that you photograph. Okay, so if we used a base 5 number system, what would be the first 3 smallest place values, with 1 being the lowest? Okay, so let's look at a base 10. Which we just did. This is our base 10 system. 10 to the 0 power. The first place is the ones place. Decimal point would obviously go here. The second place would be 10 times bigger, which is 10. And the third place would be 10 times bigger than that, which would be 100, which we can represent as 10 to the second power. So here's the lowest place value, the ones place. Then it would be the fives place. And then it would be, let's think about that. So that's 5 to the 0. 5 to the 0 is 1. That would be the first place value. The next one is 5 times bigger, because it's base 5, not base 10. 5 times bigger. 5 to the first place. So the next one is 5 times bigger. 5 to the second place. Came up with that. Good job. So this would just be a base 5 system. It would follow the same logic as our base 10 system. Yeah, it's really important to note, this is from the reading, that the role 0 plays. And consider the number 4002, which you can write in here as 4 10 to the thirds or 4 thousandths, no hundredths, no tens, and 2 ones. Without the zeros, they hold the place value. It would be hard to distinguish that without zeros. Would you know that maybe leaving a space or a lot of spaces would be the same as zeros? They would know. It'd be very difficult. So zero is a very valuable, has a very valuable role, both in place values and in representing no value. So zeros act as placeholders, place value holders, indicating no value, or a zero in a given position. This is very familiar to you, I understand that. But it's so familiar that you're going to have difficulty, most students have difficulty when we switch place value systems. And we're going to do that because the first place value system was the Babylonians. And we're going to take a brief look at the Babylonians. Because you know your base 10 system so well, it is strangely disconcerting when we switch to another base. The Babylonians, pictured here, which is modern day Iraq and Kuwait, and there's the reign of their empire, the dates of their empire, and that is almost over 1,500 years. And they're credited with the first place value number system. But they used base 60, not base 10. That means they had numbers from 1 all the way to 59, and then they regrouped at 60. So 60 was their base. 60 has a lot of, it's divisible by every number from the first 6 numbers that we have. So 60 divided by 1 is 60. It's divisible. 60 divided by 2 is 30. 60 divided by 3 is 20. So these are factors, right? Even today, there's vestiges, there's leftovers from this great empire and this great system that they built. For instance, there's 60 minutes in an hour, and that's a vestige, a leftover from the Babylonians. Likewise, there's 360 degrees, which is 6 times 60 in a circle. So we just replaced the powers of 10 with the powers of 60 in our table. That's what we're going to do. And use subscripts to denote a different base from 10. In other words, if we're going to use base 60 and we're going to say this number here is base 60, we're going to use a subscript of 60. And we're going to say, and we haven't hit it yet, this number here is base 5. We're going to use a subscript of 5, notifying us that this is a base 5 number. Now, if we just write a number like 115 with no subscript, that's our number. So a number that has no subscript is our base 10 number. Otherwise, they will have subscripts, they're called. Okay, so here's one for your book. Example 1.19a. And we want to represent these two numbers, which are base 60, in our base 10 number system. So in other words, what are these numbers as we know them? This is not 1035 because it's base 60. Well, first let's build a base 60 system up here. The first, before the decimal, I don't think they had decimals. Later on they developed fractions, actually, the Babylonians. So this would be the ones place. And that would be 60 to what power? And if you guess 0, you'd be correct. Now this is not the tens place because this is going to be 60 to the first power. That means that's the 60s place. 60 to the second power is 60 times 60, which is 2 zeros and a 36, right? So that's 3,600. And 60 to the third power, is going to be 3,600, or 60 times 60 times 60, which is 216,000. So this is the base 60 number here. We're going to convert it. Now remember, here's our place value system for base 60. A 1, 0 in base 60 means 160 and 0 ones. We would know that number as 60. So 10 base 60 is our number 60. So we're going to try to find out what this number is in our number. But I'll write it up here. It's the easiest way to do it. 1, 0, 3, 5. So that means one of these. So I have 216,000 plus 3 60s plus 5 ones. And so this would be 216,000 plus 180 plus 5. So that's 216,185. So that number in base 60 is this number as we know it in our base 10. So let's do one more here. Let's pause. I'm going to pause this and clean this up a little bit. Okay, we're going to do this one now. I'm going to put it up here. I always do that. It's 2, 3, 7. So it's 2 of these plus 3 60s plus 7 ones. So this is 7,200 plus 180 plus 7, which is 7,387. So our number 7,387 is the same as the base 60 number 237. Now the Babylonians did not use 1s and 3s and 5s. But this is an idea because this is a representation of a base 60 system. We'll see how they did it. And here are the last two parts of that problem. You can put it on pause and write it down. I'm not going to go into them. They're pretty self-explanatory when you at least see the answers. So the Babylonians were the first to have a place value system, but they only had 2 numerals. They had a symbol, like a little wine glass, that's what I call it, for the numeral 1, and like a less than sign filled in there a little bit for the numeral 10. So that's all they had. They had a 1 and a 10. And then they constructed like 1 1, 2 1s, 3 1s, all the way up to 9 1s, and then a 10, then a 10 and a 1, and a 10 and 2 1s for 12. And they had all this all the way up to 59. At 60, they would just have a 1, or like a wine glass, backwards, and a space. they did not have 0. And being that they didn't have 0, that caused a lot of problems. So basically, it's just an additive system like the Egyptians, except when you get to 60. So you could use 1 0 in place of 60, but they didn't have a 0. So that's what they had to do. It's the Babylonians. So this is our last example that you'll be responsible for taking a photograph of, writing down. So write the following numbers given Babylonian numerals in our base 10 system. So this illustrates the problem with the Babylonians and why our system is way superior, right? So here, this is just 2 10s and 3 1s, no space between them. So this is just a 23. This one here has a space between them. So these 2 10s are in the second place value, and these 3 1s are in the first place value. Let me show you what that means over here. Here's our place value system. And it goes on forever, but this is just the first 2. There's 60 to the 0 power, which is 1s. And here is 60 to the first power, which is 60s. So what you have is 20. This here is 10 and 10, so that's 20 of these. So 20 times 60 is 1200. And then 3 of these. So add 3 and I get 1203. So this number here is 1203, while this value is just 23. And the difference is they left more space between the two. And see how difficult to differentiate between the two numbers? So as in the other lessons, you're going to do this homework. This comes directly from the lecture, 1.8, 1.8b, all these here. One point 10a we didn't do, and 1.10b we didn't do. Hopefully I took them out. So here's the standard format. For each number below, state the value of the numeral 3 in standard form, expanded form, and exponential form. So I'll do one of these. Let me put this on pause. So in this example here, that 3 is, I'm going to write it in standard form, which is just 3,000. And then I'm going to write it in expanded form, which means 3,000s. And then I'm going to write it in exponential form, which is 3 times 10 to the third. So these forms are all equivalent. They're just different ways of writing it. So I'm going to leave this and this for you. I think you should be fine with number 2. We went over that. It's in the book there. And just give you an example of number 3, so you should be fine there. And maybe I'll just do 1 here in number 4. So here's number 4, and you're just taking it in exponential form and write it in standard form. Standard form is just the way you write a number, like 123. That's the standard form of the number. So let me do this one. Watch how I'm going to do it and see if you can repeat that. Otherwise, you can do it the long way, right? This is 6. Look up on your chart. That's, I think that would be 6 10,000s plus 3,000s plus 200s. But I know if you have something in the 4th place, which is a 5, you're going to have something in the 3rd place, and I don't see a 3rd place. That means there's nothing there. There's 3 in the 2nd place, 7 in the 1st place, and 5 in the 1's place. That's the number. That's how you can do it. So that's 4. Look this up. These are important. This is 10 to the 3rd, 10 to the 6th, 10 to the, every 3 it goes up by 3. 10 to the 3rd, 10 to the 6th, 10 to the 9th, 10 to the 12th. It's something you really need to know. And I think we worked on these, so you should be able to do those. This you just drop into the place value system. And you're not going to have 8 on your paper. These are exponents, and that should be simple. So that should be about it.